Sample exam 6, problem number 35. Let x be a continuous random variable with density function f of x, which is b times e to the minus bx, where b is greater than 0. If m of t is the moment generating function of x, then what is m of minus 6b? So problem 35, we need to find the moment generating function, and that is defined as the expected value of e to the tx, which then you plug it in. This is our density. Integrate from 0 to half. Well, actually first we combine the e's and then we integrate. And notice, so then we integrate, and then the limits of integration, this only exists when t is less than b. So then you plug in infinity, you get 0. You plug in 0, you get minus b to the t minus b, but then you take the negative into the bottom and it cancels. So then you plug in minus 6b into this, and you get 1/7. Number 36, let each of the independent random variables x1 and x2 have the density function f of x, which is e to the minus x. What is the joint density of y equals x1, y1 equals x1, and y2 equals 2 times x1 plus 3 times x2, and the domain on which the density is positive? So problem 36, we want to find the joint density of y1 and y2, and y1 is defined as this, y2, so you have to back solve for x1 and x2, and then the Jacobian is this, which is the derivative of y1, derivative of y2 in here at 0, except you get 1/3. So then the joint density of y1 and 2 is you plug in x1 into the density of x1. Oh, they're independent, so you can separate them. Plug this into x2, take the absolute value of the Jacobian, you get this, and here is the joint density. Now, as far as the limits or the domain of this, I always like to draw a picture. So originally, x went from 0 to infinity, x2 was 0 to infinity, or x1. So then what you do is you map the boundaries to this new area. Okay, and so let's do this one here, and I call that boundary 1, and this is boundary 2. I might have wrote that too small. So what is boundary 1? Boundary 1, x2 is 0 always, and x1 goes from 0 to infinity. So then here, x1 goes to 0 to infinity, so y1 goes from 0 to infinity. And here, if x2 is 0, then y2 goes from 2 y1 to infinity. So anyway, then this boundary maps to this boundary where y2 is equal to 2y1. And then, so x2 goes from 0 to infinity, and x1 goes stays at 0, so then that maps to this boundary. So then to be between the boundaries, being between the boundaries here, so this ends up being our limits of integration. y2 is greater than 2y1 to infinity, and y1 goes from 0 to actually y2 over 2. So this is a 37. Let x have a probability density function f of x, which is equal to 8 over 9x times 1 over 9 for x 0, 1, 2 to infinity and 0 elsewhere. What is the moment generating function of x? So number 37, we want to find the moment generating function of x. So I solve this two different ways just because I think it's informative. So by definition, it's this, and we plug it in to our probably mass function. So now the first approach, what I do is, if this weren't here, this is a density, so this integrates to 1 from 0 to infinity. So if you call this P, this would be 1 minus P, probability of success, probability of failure. So what we're going to try to do is trick this into another density type setting. So the x's we can combine to this, bring out the x in here, and then we have the minus 9, and then I multiply by 1 here. But this is a well chosen one. So if you take 1 minus this, you get this piece right here, and then we multiply it by 1. So we take this piece and the 1/9 out front of the summation sign. So notice that this times this, the 9's cancel, and we're just left with 1 over. So this is another density. Of course, for this to be a density, t has to be less than log of 9 over 8. But then this sums to 1, leaving just the piece out front. And so that is our moment generating function. Now, the second way to solve this is if we take our moment generating function, and so I skip to this step down here, and I took out the 9 and combine those. That's what this is. Now, if this were less than 1, which is this requirement, this is a geometric series. So then you take the 1/9, and then this converges to 1 over 1 minus, whatever that is. And then when you solve this and cancel, you get the same thing. So that's two different ways to solve it. Number 38. A die was rolled 30 times with the results shown below. If a chi-square goodness of fit test is used to test the hypothesis that the die is fair at the significance level of alpha equal to 0.05, then what is the value of the chi-square test statistic and the decision reached? Number 38, we're rolling a die and we want to know the chi-square test statistic and the outcome. So the null is that the observation, or the probability of rolling a 1, 2, 3, 4 through 6 is the same. We're going to roll a dice 30 times, and so this is our test statistic. So the expected number of each, expected number of 1, expected number of 2s, etc., is n times the probability of the observing that number of pips on the die, and it's constant. So this is 30 times 1/6, which is 5. And so I'm going to factor that out front, and that's what this 1/5 represents. So this is the observed. So we observed 1. The expected value is 5. In the 30 rolls for number 2, we observed 4. Expected value is 5. So this is observed for 3, observed for 4, observed for 5, observed for 6. Square all those, you get this. Add them up. Divide by 5, you get 11.6. Now the 95th percentile of chi-square with 5 degrees of freedom, which is 1 minus the number of categories, is 11.071. So we reject the null hypothesis. Number 39. A box contains 10 white and 15 black marbles. If 10 marbles are selected at random and without replacement, what is the probability that X of the marbles are white for X equal 0, 1 through 10? Number 39, it's just a simple hypergeometric distribution, and that's it. Number 40, let X be a continuous random variable with density function f of X equals 2X raised to the minus 2, where x is between 1 and 2. If y equals x to the 1/2, what is the density function of y for y between 1 and the square root of 2? Number 40, we want to find the distribution of y, which is the square root of x. So then you back solve and you get x is equal to y squared. Take the derivative of this with respect to y, you get 2y. And if we plot the region here over 1 to 2, and this is a 1-to-1 function. So if this were to go over a bigger range and end up coming back up, then it's not a 1-to-1 function, and you have to do different techniques to find this density. But since this is a 1-to-1 function over this region, this is just simply the formula. The density of y is f of x, where you plug in y squared, and then you take the times the absolute value of the Jacobian, or the which is a determinant. And then anyway, that deals with the shape of the distribution of this transformation. But you plug in the numbers and you get 4 over y cubed. Number 41, let events S and T be independent. What is the probability in terms of probability of S and probability of T that exactly one of the events S or T occurs? Now, number 41, we want to find the probability that exactly one of the events occurs, but not both. And we want it in terms of probability of S and probability of T. So if we were to draw a Venn diagram, we're going to solve this two different ways. If we're going to draw a Venn diagram, and where this is S and this is T, and we want S to happen or T to happen, but not both, then this shaded region is what we're looking for. So here, if we look at the probability of S, that's this big circle. So we got one too many. We added this, we'll have to subtract that. But then if we add the probability of T, which is this region, we just added this again, so we have to subtract out 2 of the intersection. But because S and T are independent, we can take them and break them apart, and so this is the answer based on the Venn diagram. Now, using a little more algebra, we can do it this way. So the probability that we observe S and not T, or we not S and observe T, because they're independent, we can break them apart, which is this and that, and they're mutually exclusive, so the union is a plus. Now we rewrite this in terms of probability of T. So probability of not T is 1 minus T, and then the same here, this is 1 minus S. So then you multiply those in, and you get this, which is the same equation. Number 42, let x1, x2, x3, x4 be independent random variables having a normal distribution with mean 0 and variance 1. The distribution of x1 plus x4 over the square root of x2 squared plus x3 squared is the same as that of a times y, where, now number 42, a couple notes here, that our data are normally distributed. So when you add normally distributed, you get normal. And so you get the mean, and then the variance is 2. So, and then if you square a standard normal, which is what each one of those are individually, that's a chi-squared with 1. And then when you when you add chi-squareds, independent chi-squareds, you get a chi-squared with the degrees of freedom added together. So this chi-squared 1 plus chi-squared 1 is equal to chi-squared 2. Now notice that 1, 2, 3, and 4 are all independent. So x plus 1 and x plus 4 is independent of 2 and 3, which is important in our next step. So now to develop a t statistic, we have to have a standard normal over a chi-square distribution divided by its degrees of freedom. That's a t distribution with n degrees of freedom. So if we look at this, the numerator, x plus 1, x1 plus x4 divided by its standard deviation makes this a standard normal. And we subtracted the mean, but it's 0, so we didn't put it on there. So this is a standard normal. So we've established that x2 squared plus x3 squared is a chi-squared with 2 degrees of freedom. So if we divide by 2, then this statistic is or this random variable is a t distribution with 2 degrees of freedom, which is this. So now the square root of 2 and the square root of 2 cancels, and we come up with this, which is a t distribution with 2 degrees of freedom. And that's all I have for today. I hope you liked it. Please like it and subscribe so you don't miss the part 6 to exam 6. Thanks. Bye.